Hi, and welcome to Lecture 1 of Lesson 3. This lesson is all about voltage dividers and current dividers, or Chapter 7 in your book. And what we're going to be covering today is series voltage dividers, current dividers with two parallel resistances. That just means a parallel circuit, because all parallel circuits are current dividers, just like all series circuits are voltage dividers. We're going to talk about current division by parallel conductances. As you might recall from Chapter 5, we found it easier to determine the equivalent resistance by using parallel conductance. Well, we're going to use another property of parallel conductance for finding individual current drops. Alright, we're going to be talking about a loaded voltage divider, which means a series parallel circuit. So that's a series voltage divider with a parallel load current. They tried to make this all sound so fancy when it's just stuff we've looked at earlier, but now we're seeing the application side of it. Okay, and at the end we're going to be talking about designing a loaded voltage divider. Alright, so let's just continue on. And, oops. There we go. So, what we've looked at in the past for Ohm's law and series circuits, we noticed that the total voltage equaled the current, because as we recall, current in a series circuit was constant, which means all resistors had the same current, times the total resistance. That gave you your overall Ohm's law for a series circuit. Well, now the fact that current is constant, we're going to be able to kind of express this as total voltage equals some scaling times total resistance. Basically, we're saying that the total voltage is proportional to the total resistance. And if the total voltage is proportional to the total resistance, then a single resistor, the portion of the total resistance of a single resistor times or over the total resistance times the total voltage, you should be able to calculate your voltage drop across that resistance. And that's what this whole sentence here is saying. And it's just because of the property that current is constant. Now, you can use this formula right here, across a series circuit with any number of resistances, because, once again, each voltage drop is going to be proportional to its resistance. And that resistor's proportionality to the total resistance times the total voltage is going to give you that voltage drop. And then hopefully you noticed back in Chapter 4 when we're talking about series circuits that the largest resistor in a series circuit is always going to have the largest IR drop, or the largest voltage drop. So let's have a look, say, at this one here. Alright, I have no place in this circuit am I mentioning current. There's no current involved here. I don't need to know current, because I happen to know the total resistance. 1 k ohm times 999 k ohms is going to equal 1000 k, or 1 mega ohm. And my total voltage is 1000 volts. Basically, that's saying that I'm going to have 1 volt per kilo ohm. So if I want to know the voltage drop at R1, I've got 1k over 1000 k, which is going to equal 0.001 k ohm times 1,000 volts, it's going to equal 1 volt. That's just the way it is. So, in this case, I've got R1, which my pen just quit working on me for some reason. Working on it, trying to get it back. Looks like we're going to have to do a quick pause. So we'll come over here, we'll come over here, and then we'll come over here. Okay, back again. Everything's working like it should now, hopefully. Alright, looking at R2, we've got 999K over 1,000K, which is actually going to come out to 0.999 times 1,000 volts. We're going to equal 999 volts. So you see, it is proportional to the proportionality of the individual resistance over the total resistance times the total voltage. Now, the interesting thing here is those values can change, okay? So we're looking at 1 ohm versus 999 ohms. Excuse me. We're just changing these values to 1 ohm and 999 ohms, which is going to equal 1,000 ohms. Well, in this case, for R1, 1 over 1,000 is still going to equal 0.999. Pardon me. 0.001. In this case, 999 over 1,000 is still going to equal 0.999. So my voltage drop, even though I've changed the totals of the two resistors, they still come out to the same proportion. This is 1/1000th, and this is 999 1,000ths. So they're going to still have the same voltage drop of 1 volt and 999 volts. So we are just looking at the proportionality of resistance to the overall resistance to give us the voltage drop. Now, when we start looking at bridge circuits, this is going to make more sense to you, because that's how we will balance out a bridge circuit. Alright, and now I've got to go down to the next slide. If I can get it to go down to the next slide. There we go. Alright. Okay, yes, I'm in the right place. Alright, here we have your basic series voltage divider circuit. Now remember, with the ground tap there, that is just saying that those 2 points are connected. That ground there and that ground there indicates that these 2 points are connected, and your negative side of your power supply is considered your ground. So all these are going to be positive measurements. And here we have 10k ohms, 7.5k ohms, 1.5k ohms, and 1k ohm, or a total resistance of 20k ohms. Now, The voltage being tapped at point A is basically just the voltage drop across R1. You see R1 at 20 or at 10k ohms, 10k over 20k is going to equal 0.5 or 1/2. So we can expect of the total voltage, half of it is going to be dropped at R1 or 12 volts. And you see, I'm not even doing any real calculations here. I'm just sort of glancing. This one I will do a real calculation on because just off the top of my head I'm not going to do 7.5. I think it's like 3.5%. But so 7.5k over 20k is going to equal, let me bring up my calculator here real quick, and 7,500, whoops, 7,500, there we go, over 20,000 equals, well, 37.5%. So we'll multiply that by the total voltage, 9 volts. So let me get my stylus working here again. We had 12 volts there. We had, what did we say, 7.5 volts there? Happens every time with this new program. 9 volts. 9 volts is what we had. Go back to my annotations. 12 volts, 9 volts. Okay, 1/20th, so 24 over 0.005. See if that's 9 volts. And I got 12 volts to go. Oh heck. Back to my calculator. That's what happens when you do this at the end of a day. Clear. 1 divided by 20. 1 divided by 20. Let's say again, 20 equals 0.05. All right. Times 24 equals 1.2 volts. Bring that back up. 12, 9, 1.2, 1.8 will be our voltage drops at points A, B, C, and point G if we should have been a D coming out here. I don't know, point C. Point C is good. Stupid me. Let's see here. Come grab my eraser. Let's get rid of that. Go back to my pen. Alright. So I just followed that simple formula. Whoops. That one. Why have I still got an eraser? I don't want my eraser anymore. Guess I gotta erase everything before it'll let me get rid of my eraser. This is a new program, like I said. Looks like I need another new program. There we go. Alright, just following the formula. R over RT times VT. And that gave me my 12, 9, 1.8, and 1.2 volts. Each of these voltage drops easily calculated. for my points A, B, C, etc. Once again, at no time did I bother adding up different resistances. I didn't have to calculate current. I was just able to use the proportionality to the total resistance of each resistor to get its proportional voltage drop. Easy as that. All right, and here we're going through each resistance. All right, they're starting down here and performing the same calculations I just did. Oh, the thing I forgot. Okay. It was easy to calculate just the voltage drop at point A because I was going across R1. At point C, I just went across R4. Getting point B, I have to either add the 2 voltage drops there or the 2 voltage drops here. Okay, in this case I had 1.8, pardon me, subtract the 2 voltage drops here, because got to remember we're going down to ground, or add these 2 voltage drops, alright, because we're measuring B to ground. So it's across these 2 resistors for B, but C is a single R4, A is a simple R1. I hope I didn't just confuse you there. Yell at me if I did. So let's try doing this again, only we're going to go slowly. Alright, I gave you the voltage drop across each resistor. So we had, where am I? Oh, there we go. We had 12 volts here. We had 9 volts here. Pardon me. 1.8 volts here. 1.2 volts here. If I want the voltage drop across or at point A, and I'm measuring A to ground, because of course that's how the voltage drop would be measured, I then have 9 volts plus 1.8 volt plus 1.2 volts, or 12 volts at point A. If I'm measuring the voltage at point B, I've got the voltage drop across R3 and the voltage drop across R4, or 1.8 plus 1.2, 3 volts. If I'm looking at point C, I'm looking at the voltage drop at R4 only, 1.2 volts. Because all these measurements are in relation to ground. What I originally said about it just being the voltage drop across R1, I happened to get lucky there. Because I was just thinking that point to that point, which is incorrect. It is actually between point A and ground. That's how the voltage taps are being measured. Alright, now we'll continue on. Alright, now in a parallel circuit, voltage is constant, and you're changing current and resistance between branches. And unfortunately, while that's fine and dandy, but resistance and current are not proportional. The only difference is when we have 2 resistors. And in this case, if we're looking for the current at resistor 1, we are going to take the proportionality of resistor 2. Once again, current is inversely proportional to resistance. So the branch with the smaller resistor is going to have the higher current. So we're taking the inverse proportionality with a 2 resistor set here. So for the current at resistor 1, we take resistor 2 over the total R1, R2 and multiply it by the total current. And that's going to give you the current at resistor 1. So in a 2-branch system, your two branches are going to be inversely proportional. And this formula can only be used for a 2-branch resistance. It's not my favorite formula to use. My favorite formula to use is using conductance, because conductance you can use for no matter how many branches you have. So in the case of this here, two resistor set, I want to know what the current at R1 is. Well, I'm going to find out what the proportionality is of R2 over the total resistance. In this case, 4 ohms over 6 ohms is going to equal 2/3 times 30 amps. Okay, because your total current here is 30 amps. So 2/3 of 30 amps is going to be 20 amps. That's going to be flowing through the R1 side. To find out the current going through resistor 2, I'm going to take the value of resistor 1 and its proportionality of total resistance. So 2 ohms over 6 ohms, I'm going to end up with 1/3 times 30 amps. So my current flowing through R2 is going to be 10 amps. And that will account for my total current of 30 amps. As we know, parallel circuit, current divider. This is great for a 2 resistor set. It doesn't work for any other configuration. Oops, let's try that one. Now, current division by parallel conductance. Let's go back to Ohm's law. V equals IR, which means with a constant voltage, I is going to equal 1 over R. So the relationship between current and resistance is inverse. The relationship is inverse. Now let's look at conductance and resistance. Resistance is equal to 1 over conductance, or conductance is equal to 1 over resistance. So if we substitute conductance here, we get current is equal to conductance. We have a direct relationship between current and conductance. And now you can treat it just like you did resistance and voltage in a series circuit. So if you want to know the current flow through any given branch, and let me see if I can, there we go. Here we have 3 resistors, one at 10 ohms, one at 2 ohms, and one at 5 ohms. Well, my conductance for the 10 ohm is 0.1 Siemens. My conductance for the 2 ohms is 0.5 Siemens. My conductance for the 5 ohm is 0.2 Siemens. So my total conductance is going to be 8 Siemens. So if I want to find the current flow through R1, the proportionality for R1 is 0.8 Siemens, pardon me, 0.8 Siemens is 0.1 over 0.8, or 1/8, or 0.125 times the total current. Total current is 40 milliamps. Okay, it's going to equal 1/5 or 5 milliamps. But let's go ahead and it's going to equal 1/5 of 1/8 of 40 or 5 milliamps. And they give us our answer right here. In the case of R2, and let's go ahead and get rid of all these marks on the page, because I won't be able to write anything else if I leave those marks on the page. For some reason, if I'm going to change a mark, I got to change them all. So maybe it's not the best program in the world. Okay. In the case of R2, I've got 0.5 Siemens over 0.8 Siemens times the total current, 40 milliamps, so bringing out the calculator again, .5 divided by 0.8 times 0.04 equals, that's 25 milliamps. And gee, it actually works out, the math actually works out right there. And finally, I got to re-annotate that, 0.8 Siemens. So I end up with, for R3, 0.2 Siemens over 40 milliamps. I'm going to end up with 1/4 of 40 milliamps, or 10 milliamps. Now notice, R1, 10 ohms, it's got 5 milliamps. R3, 5 ohms, 10 milliamps. R2, 2 ohms, 25 milliamps. The branch with the lowest resistance gets the most current. But once again, this is going to work no matter how many branches you have. It'll work for 2 branches, it'll work for 12 branches, it doesn't matter. And the lowest resistance gets the most current. In a series voltage divider, the highest resistance gets the largest voltage drop. It's inverse and parallel. The lowest resistance gets the highest current flow. Now, why didn't I teach this method back in chapters 4 and 5? Well, you got to understand the basics. You got to work through Ohm's law and the how to calculate equivalent resistances before we can jump ahead and get the easy way. You know, it's just the building blocks. All right, and I'm going down. There we go. And once again, this is the same calculations we just made a minute ago. And you see, if we did the Kirchhoff's current law, we would see that 5 milliamps plus 25 milliamps plus 10 milliamps is going to equal 40 milliamps. You can always check your answers when you're done. Okay, here we're getting into this series voltage divider with parallel load current. And we're going to what we're seeing here is how things change as you add a load, okay? So we start out with a circuit where we have R1 at 40 kiloohms, we've got R2 at 20 kiloohms, and 60 volts. Alright, we got 2/3 of the voltage at R1, we got 1/3 of the voltage at R2, so 40 volts at R1, 20 volts at R2. Everything's going on nice and easy. And then we add a load, RL. This can be a machine, this could be a speaker sitting out here. It can be anything. It is some load on the circuit. That's why we don't give it a resistor number, we give it a load reference. And when we add this load out here, all of a sudden our circuit changes. Okay, in this case they put a 20 k ohm load, which changed this equivalent resistance to a 10 k ohm resistor. So all of a sudden, instead of having 60 k ohms total load in the circuit, we have 50 k ohms, which means the voltage drop is going to go up there. And instead of having 20 k ohms, we're down to 10 k ohms, which means our voltage drop across this section is going to change to 12 volts. And this becomes our equivalent circuit as soon as we hang a load on it. We never design a voltage divider starting with just the series circuit. When we're designing a voltage divider, we are designing from the load and the final resistor, and we work our way upward from there, knowing what we need to drive the load, what kind of voltage we need, what kind of current it's going to demand. So it's not like we're going to start with this circuit and then hang something on the outside here. We're going to design this circuit with the load in mind, so we don't end up changing the total design of the circuit. Okay, and they're just showing you the math behind the previous circuit. Alright, so how are we going to design this once again? Well, first I'm going to bring my pen back. I had a little minor malfunction, but we're back to working now. Okay, we are going to once again design our voltage divider, first considering the current that's got to flow through the voltage divider portion. And this is known as the bleed current. And that's what we have here, the bleeder current. Now with that in mind, we take into account the load and its voltage requirements and its current requirements. So I have some specification for the bleeder current, and that is generally about 10% of your total current is generally your bleeder current. So knowing what my total current is going to be is a good idea ahead of time, and that's part of the specification of a design. So I'll know what the load current's going to be, and I know what the voltage requirement of the load is going to be. So that's going to help me select my first resistor in the voltage divider. And then the next resistor I know is going to have to take the bleed current, which is the constant, plus the load current. And if there's another load hanging out here someplace, there's also whatever the current requirement is of that load. And of course, that load would then be added on to the total load onto the main trunk. So this is how we're going to design. We're going to work our way from the first resistor in the voltage divider to meet the needs of the load, and then work our way through the rest of the voltage divider from there. And this is what we have shown here in this example. Alright, in this case, let's see, let me get rid of that thing. Okay, in this case, I have R1 and I have load F. Now, my voltage requirement for load F is 18 volts, and it's going to want 36 milliamps worth of current. In this case, I know my total current is going to be 300 milliamps. Now, I won't necessarily know that off the top of my head. I may have to do some calculations to figure out what it's going to be. But in this case, my total current is going to be 300 milliamps. So I know my bleed current is going to be something like 10% of my total current. So R1, I know it's going to run at 30 milliamps, and it has to drop 18 volts. So, where am I going to go from there? Well, R1, 30 milliamps, 18 volts. Oops. So 18 volts over 30 milliamps. 18 volts over 30 milliamps is what? 18 divided by 0.03 equals 600 ohms. So R1 here is going to be about 600 ohms. I don't care what I'm hanging out here. For my voltage divider, R1 has got to equal 600 ohms, because that's what's going to give me 30 milliamps at 18 volts. Now R2 is going to give me, has got to support that 30 milliamps and an additional 36 milliamps, because remember, current flow from both sides. So R2 is going to have 66 milliamps running through it, and my voltage drop between point E and point G has got to equal 40 volts. Well, I know R1 is going to account for 18 of that, so R2 has got to account for 22 volts of that 40. So now it's as easy as 22 volts over 66 milliamps. So my resistor R2, if I go back to my calculator, I've got, what did I say, 22 volts divided by 0.066 equals 333.333333 ohms. So we're going to say 333 ohms. It's not going to be exact. It won't give us the exact number we need. If we go to precision resistors, which actually would be used in this situation, we can get 333.33 ohms. All right. Then R3 is going to have this 66 milliamps, and then the additional 54 milliamps required by load E. So R3 is going to see 120 milliamps of current, and of course we have 40 volts, and our original source is 100 volts, so he's going to be dropping 60 volts. Right? So if R1 and R2 are dropping 40, R3 has got to drop 60. So 60 volts over 120 milliamps. Get my calculator going again. 60 divided by 0.12 equals 500 ohms. So this guy is going to be 500 ohms. 333.33 and 600 ohms. Okay, then my load D here, of course, is going to want to see the entire voltage source at 100 volts, and he's going to use 80 milliamps. So at point D, I've got this 120 milliamps flowing up through the voltage divider network, and then I've got another 80 milliamps. Oh, pardon me, I have another 180 milliamps. So my total trunk current is 300 milliamps. So I have to make sure that my voltage source will supply me with 100 volts at 300 milliamps. Now what if I didn't know my total current? Well, I know that I've got 180 milliamps. I know I've got 54 milliamps. I know I've got 36 milliamps. That is my minimum requirement. And that should bring me to about 270 milliamps. To figure my total current then, is going to equal my bleeder current plus 270. Well, I know my bleeder is going to equal 0.1 total current, so I just stick that back in there and I end up with 0.9 ET equals 270. So 270 divided by 0.9. Oh, got to get my mouse working again here. 270 divided by 0.9 equals 300 milliamps. milliamps. And then if my bleeder is equal to 1/10 that, my bleeder is going to equal 30 milliamps, and there we go. The 10% of total current is a rule of thumb. Maybe not an absolute rule of thumb, but it is a basic rule of thumb if you're designing a fixed loaded voltage divider such as we have here. All right, now let me get rid of that thing. Okay, and we just went through all this math. Let's get the pen working again. Yes, we went through all that math. And we went through that math. Maybe I need to have my pen off the tablet for it to work. Oh, and we appear to be out of slides. There we go. So we did come up with all the math here, with R1 having the bleeder current of 30 milliamps. Then going through R2, we have the 36 of the load plus the 30 milliamps. Going through R3, we have the 54 milliamps of the next load plus the 36 of the original load plus the 30 milliamps of the bleed current. Gives us 120 milliamps. We saw that voltage 1 was 18 volts to ground. Voltage 2 was the 40 volts. However, 18 of that volts was dealt with by R1, so I had R2 needing to make up the 22 volts. And finally, V3 was 100 volts at point D. Well, 100 volts minus the 40 volts being dropped between R1 and R2 left us 60 volts for R3. Which, as you saw, gave us our totals, which once again, we already did that math. And that's Chapter 7 in a nutshell right there. So, to calculate, and let's see if I can't throw in another slide here real quick. Let's get rid of that. Let's get rid of that. That way I can just write on it easier. All right, let's do a quick. What was important here? Well, we learned that resistance in a series circuit, a single resistor voltage, the voltage drop across a single resistor, is going to equal the proportion of that resistance to the total resistance. Times the total voltage. Because in a series circuit, voltage and resistance are directly proportional to each other. In a parallel circuit, your current drop across a specific branch is going to equal, since current and resistance are inversely proportional, and resistance and conductance are inversely proportional, just as we discussed back in Chapter 5, then instead of using R to calculate, we're going to use conductance. And therefore, the current in a specific branch is going to equal the proportionality of conductance of that branch to the overall conductance times the total current for the circuit. And that will give you your current flow through that branch. So those were important points. And then remembering designing a loaded voltage divider, got to have at least 2 resistors in the series circuit to give you a voltage divider. We want to calculate the bleed current. All right, let's see if I can do that without all the interruption. Okay. Where was I? I was in a loaded voltage divider, designing. We want to calculate the bleed current. We need to know what the load voltage requirement is. And the load current requirement. So I need to know if it's going to run at 12 volts and 40 milliamps or 2 amps or whatever. If I know those, I can calculate my bleed current, because my last resistor in line here, the current going through him, is simply going to be your bleed current. The current going through your next resistor is going to be your bleed current plus your load current. And then you can calculate the resistance on that guy. Of course, you're going to want to know your total voltage. Once you calculate all that, you'll know what your voltage source has got to be able to produce as far as current goes, or what current it's got to support. And Chapter 7 is pretty much as easy as that. I beg you, I urge you, work on some of the problems in the book. All the answers are in the back of the book. So at least on to the evens or the odds, I'm not sure on this edition. Practice by working through those problems. Practice makes perfect. If you can do those problems, you can do any problem. Get into the exercise that I assign and that I grade, and that being your first shot at it doesn't cut it. You end up getting 6s instead of 30s. So that not only impacts your grade, but it also impacts your ability to keep working forward. And when we get to, say, Chapter 10, where we're working with some more design tools, you need to be pretty well versed in all these equations that we've been working on. So you got to practice. I've also given you the opportunity, since everybody got their work done early for the previous lesson, you can go back and try those exercises over again. Number one, it's good practice, it's good exercise, because that's what exercises are for, and you'll still get graded on, because there's only 4 of you left in this class, which means it's much easier for me to take care of grading papers. It's not like I'm grading 14 papers every week. So that is about it. Now, I did set up a loaded voltage divider circuit here, but I don't want to muddy the waters with that one at the moment. So maybe next week or the week after, I'll throw that up as a bit of a review. But for this week, just take the basics, take care of the book, and that's about it. I will be in the office to answer questions on Wednesday. If you're not CONUS and you need some extra time, figure out when you can be available, and I will do what I can to make myself available on your schedule. So don't forget that. And that's about it. I will be back in on Wednesday. I'll see you then. Bye.